So, hello everyone. My name is Dimitris, Deep Learning with Python, Chapter 7. Lots of ground to cover, so let's start. Working with Keras, a deep dive it will be. So let's see the chapter contents. First of all, we will see how we can create Keras models, but using different ways. We have already seen the sequential class. We will see the functional API and the model subclassing. After that, we will see how we can use the built-in Keras training and evaluation loops, and then how we can write them from scratch. And also we will experiment with some ways to change the whole pipeline. So how we can add callbacks, how we can have custom metrics and this kind of stuff. So let's embrace and start. First of all, there is a big spectrum of workflows that Keras supports. And the whole principle of Keras is the progressive disclosure of complexity. What this means is that it makes it easy to get started if you have something quite simple as an experiment. And yet it's possible to handle quite high complexity use cases. So if you have something very simple, you use sequential, for example, with a starter feed, compile, evaluate, etc. methods. If you have something more complicated, you can get more in depth, you can change things, you can make custom things, you can inherit. We will see in more detail what exactly you can do in each case. And the idea is that it spans from very simple to very flexible. So, first of all, regarding the models, there are different ways to build a model in Keras. We have already seen the sequential model, which is more or less a list of layers, so like Python lists. Today, we will see two more methods, the functional API, which is a graph-like structure, and the model subclassing, which is quite low level, but it gives you full control for everything. And here you can see a figure. If you have something quite simple or you are a novice user, you can use the sequential API. If you want something a bit more complicated, you can move to functional API, which is what most of the people actually use. If you want to go more in depth and do something strange, you can use the functional API, but with custom layers, custom metrics, custom loss function, custom callbacks. And if you want to do something that for some reason functional API does not support, you can always subclass the Keras.model, and this can do almost everything. Now, let's start with the easy one, sequential model. We have already seen this, so we will go through this fast. We import Keras and layers, and this is the way you build it. So Keras.sequential, and you provide a list of the layers. So layer.dense, for example, like this. And the final model will be a model with these layers one after the other. So something like this, nothing new here. Another way to build a sequential model that we have not seen yet is to first create the model and then use the .add method in order to add layers. So same model as before, but with different writing. So here you create an empty sequential and then you add new layers. Now, this the first time that when you build a model, you don't have actually the model already. When you construct the model, it's not built. It's not, you don't give any information regarding the shape, right? We didn't define what is, for example, the input shape for the model we just built. And for this, you have to do one of two things, either run the model on a tensor so that the model builds the weight of each layer, or you can call the .build method and pass the input shape. So again, at the beginning, when you create the model, there are symbolic tensors, but they are not actual tensors. They don't have the shape. You have to define the input shape, and this is one of the two ways. So model.build, and you pass input shape, a tuple. The first can be none if you don't have a fixed batch size, and the second one will be whatever it is, or third one if you have more dimensions. And after you do this, you can call model.weights because now it will have created the weights. Before this line, without this line, will throw an error. So here you can see that the model has already built. Apart from this, you can have access when you use sequential method to some more tools, like for example, the summary method. Summary is very useful and it gives you access to the layers and more information regarding the structure of the model. So let's see this one, model.summary. It prints out this kind of information. So we start with the name of the model, and then you have the layers. So each layer by name and by type. So we have 2 dense layers here. And you have also information regarding the output shape. And since the model is already built, then we have access to the number of parameters, which means that we know, for example, that here we have 256. Why? Because we had 3 features as input shape. And it also provides information regarding the parameters. So how many total parameters, how many of them are trainable, and how many are not trainable. So again, very useful for easy debugging in case you are not sure about something regarding your model. Another important thing is that, well, quite important, is that you can name both the model and the layers. So here, when you build the model, you can pass the argument name, for example, my example model, and the same for the layers. So first layer, last layer, etc. Again, we built in order to use the dot summary. And here you can see that it uses the names that you passed. Now, this is not very useful. You think it's not very useful right now because, okay, it's just different names, but it will be more apparent why this is useful when we will use the functional API, where you can use specific layers for specific reasons. Now let's move on. Specifying the input shape of the model in advance. Up to this point, when we built a sequential model, we didn't define the input shape when creating. We used it either run on a tensor or use the .build method. But actually, you can just use the Keras.input layer to define what will be the input shape. And in this case, you don't have to write the batch size. So you only provide the dimensionality of the sample, not of the batch. Yet you have to provide it as a tuple, and this is why we use this way of writing here, even if it's only one dimension. So same as before, but here we provide an input shape, and now we don't have to build it. It's already built, so we can use summary directly. This was more or less regarding the sequential model. Again, it's something we have already seen before. And when you use this kind of way, you can also add layers afterwards. So it's not like you build the model and it's fixed. If it's sequential, you can use model.add and add a new layer, and then it will be visible also the summary. As you can see here. So the new layer has been added. So quite useful for simple cases. Sequential is a very good way to go. Now, if you want something a bit more higher level, you have to move to the functional API. So let's see what is this functional API. And actually, this is a proposed way to build models in Keras. So the sequential is very good, very easy, but quite limited. First of all, it only supports one input and one output. The functional API is a way to build a model like a graph. So you can have multiple inputs, multiple outputs, and you can have different ways to combine to connect these models. It's actually like playing with Lego bricks. And if you get used to it, it's quite fun. I mean, it's really like playing with Lego bricks. Let's see a simple example of this functional API by writing with functional API what we built before with the sequential one. So this is the way you do it. Here we have the definition of the layers. This part up to here is the same as before. But now we take the output of this layer. And the output of this layer, these inputs here, will be a symbolic tensor. Okay? It's a symbolic one because it doesn't have real numbers inside, but it holds the information regarding the type, the shape, how it was built, etc. And then we use this one as input to another layer. So this definition of layer, again, this part that I highlight is the same as the sequential, but this time we call this layer on a symbolic tensor. And this will return another tensor, the features. And then we use this as an input to the next layer that we want to combine. And we take another tensor. And the whole idea is that in the end, you call this Keras.model. And here you pass two arguments, the inputs and the outputs. Again, this will be tensors, okay? So for inputs, in this case, we have this tensor, will be the entry point of the model that will go through this one, will return this, and this will be the exit point, okay? So this way, we can build a model with this as input and this as output. Again, this model is the same as the sequential we built before with two dense layers. Now, if we build it like this, you again have access to everything we talked about before. First of all, I mentioned the notion of symbolic tensor. So the output of this layer is a symbolic tensor, this input. And this input has a shape, for example, 3 in this case, and the type. In this case, it's float 32 by default, okay? And the same holds for the other tensors. For example, this tensor, this symbolic tensor, which is the output of this layer, run on this tensor, the inputs tensor, is again another symbolic tensor that has a shape, which is in this case 64, the dimensionality, and it has a D type, a data type. And again, you have the outputs to be another tensor, and this is how you build the final model. So if you get used to this way of connecting layers, it's very, very, very powerful. Now, let's continue and see how we can use the summary method on the functional API models. It's more or less the same as before. We have the name of the model, and we have the list of the layers, the type of the layer, how many parameters, what is the output shape, trainable, non-trainable, and total parameters. So this part is the same as the sequential. Now, the example that I described before was more or less doable with the sequential, so you don't see what value can it add. Now we will see an example that you cannot do with the sequential model. So we will see a multi-input, multi-output model. Let's see the scenario that we will be based on. So let's say that we have to build a system that ranks customer support tickets by priority first, and then route them to the appropriate department. So let's say we have main support departments and we have calls or tickets, and we want to route them to the correct department. And also we have to prioritize them, okay? And we have to build a model that does this thing. So the inputs will be the title of the ticket, okay? Let's say text, and the body of the ticket, again, text. And we can add some tags, okay? Let's say we have 100 tags and some of them are enabled for each ticket. So this is the input information, and we want to output two things. One will be the priority score, so a number between 0 and 1. And the second one will be which department. So let's say, again, we have, I don't know, 4 departments, and we want to see at which one of these 4 we want to address this ticket. Now, regarding the technical information, I write here text input. In reality, we will use a multi-hot vector, so a fixed vocabulary size, let's say 10,000 words. If the word appears in the title, for example, it will be 1, otherwise 0. And the same holds for the text body. What else? So the output will be for the score, priority score, a number between 0 and 1, which means that we are going to use sigmoid output. Now, let's see how we will encode this scenario to a model, okay? First of all, we have to define some parameters. For example, the vocabulary size, 10,000 words, how many tags we can choose from, 100 tags, and we have 4 departments, okay? So these are the parameters. And this is how we will build the model. So these are the layers, and this is the final model. We start with the inputs, okay? We have 3 input layers. The first one will be for the title, so vocabulary size, 10,000, either zeros or ones, and the same for the text body. And then we have the tags to be some out of the 100. So these will be the inputs for the model. Then the next thing we do is concatenate this. So we have this layer, the concatenate, that takes a list of tensors and returns a concatenated tensor. So we apply these layers.concatenate on this list of tensors. Be careful here, all of them, of course, have to have the same number of dimensions, and we get this symbolic tensor. And then we pass this through a dense layer that outputs a fixed 64 embedding. So we pass this one here, and we take this as the output tensor. So now we have to create so these are the hidden layers, and we have to create the output tensors. So the first output tensor will be the priority tensor, which will be again a number between 0 and 1, so one number, and between 0 and 1, which will be activation sigmoid. And we apply this on this feature, on this 64 size tensor. So this is the first output, and this is the second output. Which department? So we have again 4 departments, one of them will be correct. So we want a dense layer with 4 outputs, and we want softmax. The same way we had the output with 100 digits, if you remember the MNIST dataset. And be careful, we apply this again on features, on this tensor, okay? Not on this one. And when we want to build a model, again, we have to define the inputs and the outputs. So the input tensors will be these 3, the title, the text body, and the tags, these 3. And the outputs will be the priority and the department. So all this scenario, this complicated scenario, can be encoded using the functional API, quite easy if you get used to this way of writing. Now let's see how we can train it. So let's create some dummy data. Let's say we have 1,280 samples. Here we just create random numbers for the inputs and the targets, okay? And we just compile the model. We have already built a model, so we compile using an optimizer. Be careful, since we have 2 outputs, we want 2 loss functions. So we pass a list, and each loss will be for the corresponding output. So this will be for the first output, this will be the loss function for the second output. The same holds for the metric. So we'll provide a list of lists. The first list of metrics will be applied for the first output, and the second one for the second output. And again, for the data with model.feed, we provide the list of inputs, the list of targets, and the same holds for the evaluation and the prediction. We provide the lists for this if we have multiple, okay? So we see that it runs, which is the important thing. We don't care about the performance right now. As long as you understand how it works. Again, we build a model, we define the inputs, the outputs, and the internal structure of the graph. And when we compile, fit, evaluate, etc., we use lists of inputs or outputs or losses or metrics, depending on how many we have. So let's say, this was one way using lists. Another way to do it is if we know the names of the layers, the names of the tensors, is to compile, fit, etc. using dictionaries. So instead of lists, we can provide dictionaries with the names of the tensors, the input tensors or the target, the output tensors. The same exact thing as before, but this time we provide dictionaries instead of lists. Okay, and you can see that this works. This is just a different way to write the same thing. Now, what is the power of a functional API? We already mentioned that, first of all, you can build something that has multiple inputs, multiple outputs, that you cannot do it with a sequential. Now, the good thing also with functional API is that it's a fixed data structure, which means that you can access the structure, you can inspect the layers, you can inspect how they are connected, and also reuse previous graph nodes. And this second one is very important, especially if you want to use pre-trained networks. And we will see how we can do this. A very useful function for Keras, so keras.utils.plotModel creates an image of the graph of your model. So again, every functional API model is a graph, which means that you can plot this graph. And this is how you can plot the specific graph. And you can see that you have the 3 inputs, very well displayed with arrows, etc. So you have 2 intermediate layers, the concatenate one, the dense one for the embedding, and 2 outputs. And if you want, you can also turn to true the show shapes. And in this case, you will also see what are the shapes of these tensors. So you have here, for example, the input layer that takes as input 10,000 and outputs 10,000, because of course it's an input layer, doesn't change anything. The concatenate takes these 3 and outputs 20,100 dimensions tensor. And the dense takes this, outputs 64. The priority one takes this as input and outputs 1, and this outputs 4. Okay, so all the information, almost all the information you need is depicted here. It's again very useful, especially if you have big models. This way you can see, okay, there is a false block that shouldn't be connected there or something like this. It's very useful for debugging. I mentioned before that a very powerful thing with this functional API is that you can actually retrieve the inputs or the outputs of a layer. And first of all, let's see how this works and then why this is important. With model.layers, you can get a list of the layers in this model, okay, all the layers of the model. And here we can see that we have 3 input layers, then 1 concatenate, and 3 dense layers. Now, each layer has the input and the output tensor, 1 or more, okay? So for example, layer 3, which is 0, 1, 2, 3, the concatenate 1, let's see what is the input for this one. And you see that it has a list of 3 tensors as input for this layer, okay? So you have this information visible. And also you have what is the type, what is the shape, and from which layer it was created. And you have also the output. For example, this one outputs something with this shape of this type and the name of the layer. This is very important because now we can make use of these input or output tensors. Let's see an example. Let's say that we want to create a new model by reusing the intermediate layer outputs. What does this mean? So let's say we have the previous model, we built it, we trained it, we implement it, and it works very good. But what we want is also some more information. For example, we want to estimate how long it will take for a given ticket, okay? So we have 3 difficulty ratings, the quick, medium, and difficult. And we want the model to predict whatever it predicted before, plus this one, okay? Now, what we have to do is we don't have to build the model from scratch. We can reuse the model graph as is. And we can say, okay, we want the output of the layer 4, so the 5th layer actually. And this is the symbolic tensor of this layer. This is the 64, if you remember, from the dense layer. And then we want to feed this to a new layer, let's say the layer dense, that will have 3 outputs, the difficulty. That will be softmax because only one of 3 is correct, okay? And we create this layer, we feed this symbolic tensor, and we get a new symbolic tensor. And we can use this new symbolic tensor as output. So instead of having 3 inputs and 2 outputs, now we have 3 outputs, okay? And this new model can be built. It can be built because it already knows how to connect these 3 with this new one. It knows that it has to go through the concatenation, through the dense layer, and then through the difficulty. So all the information remains. And this is very powerful, again, especially if you want to reuse something and add another head to the multi-head model. This is all you have to do. Take the output that you need, add whatever you need. You can add more layers here and create the model with the same inputs and the new list of outputs again. And you can actually exclude. So let's say you don't need the priority anymore. You can remove it. The graph will be built again, okay? So if you do this and you have the weights for the previous layers, you don't have to train it from scratch. You can use the previous weights for the existing layers and you can train only the new head, for example. And of course you can plot it. So let's plot the new model now and you see that it has 3 outputs in this case. You have this new difficulty one. Now, let's move to the next one, the subclassing model. So we saw the sequential and the function API. Now we will see the subclassing approach. And this approach is to create a class of the model that inherits from the Keras.model. So you have to define 2 things, the constructor, the inner dunder method, and the call not dunder method, just call, not with the 2 thingies. Now, for the init, first of all, you have to initialize the constructor of the superclass here. Okay, don't forget this one. And here you will define all the layers that belong to the model. You don't define the layers that are, for example, the input layers, because you don't use them here. You have to define the concatenate one, the dense one, and the second dense one, the output, for example, for the priority, and the output for the departments. So you define these ones. You don't have to pass any information regarding the input dimensionality here. So these layers now belong to the instance of this class. And you can call, you have to write also the call method. Now in the call method, the forward pass will be implemented, which means that you take some inputs and you provide some outputs. Now, in this case, let's say that the inputs is a dictionary, so you can retrieve the tensors. So these will be actual tensors, not symbolic tensors. Here we don't have symbolic tensors like the functional API. And you can use the existing layers however you want to pass the inputs. And you can have something like this, which is fixed, or you can have loops, you can have clauses, you can have if, else, etc. You can do anything you want inside here. Because this doesn't produce a graph, a fixed graph. This can be fluid. This can do anything you want. It's the lower level you can get using the Keras.model. And again, here you get the outputs, you pass them however you want, the same way we saw in the function API with the parentheses, and then you return whatever you need every time, okay? So let's see how this will roll out. We construct an instance from this class, and then we take from this model, we run this on this dictionary of tensors. Again, these are NumPy tensors, and it can handle them, and it will return these 2 tensors. So this was a simple example of how you can subclass from the Keras.model class. You can write the call method to do whatever you want. And the good thing is that you have all the good things we saw before come directly because you inherited from the Keras.model. So you have the compile, you have the .fit, .evaluate, and .predict come as is. You still have this functionality, although you can write your own call function, which is very important. Of course, you cannot have everything, so it doesn't support, for example, the summary or the plot model method and functions. And this is because the functional API, again, is a data structure. The functional API creates a graph. Subclass of the model class is not any data structure, it's just bytecode, it's just Python code, it doesn't have something fixed. This is why you cannot plot any summary, because internally, again, the structure can change at every, depending the inputs, for example. And you can not use, of course, plot models. So things that are useful like compile, fit, evaluate, predict, you can still use them, but some things like summary and plot model, you cannot use them for subclass model. Another important thing is that you can mix these types. So you don't have to choose only subclass or only functional API or only sequential. For example, you can create a functional model that includes a subclass model. So you can create a very simple, like this one, classifier with one layer. Okay. Again, you have to inherit from Keras.model, run the constructor, do whatever you want here, and write some call function that just calls a dense layer. And here we have the definition of a functional API model, the Keras.model. And we can use these layers as before, but now we can use this model as a layer. And we can call this symbolic tensor on this model, and we can get whatever outputs come from this model. And we can use these outputs tensors within the Keras functional API model, which is very powerful because we can have something quite tricky, a custom classifier, for example, and yet we want to use everything else from the built-in Keras layers, for example. So we can mix these two. And the good thing is that we can actually do also the opposite. So we can have a functional API model like this one here, and then we can use this inside the subclass model. And we can use it, for example, like this. So it's not one or the other. You can actually mix these two styles. Again, this is quite powerful and gives you very great flexibility on what you want to do. You go as deep as you want, or as you have to, actually. And it's important to remember to use the write tool for your case. Generally speaking, functional API is the better way to go. Most of the problems are not very simple that you can use sequential. And in most of the cases, you will not need to have a subclass from the Keras.model model. Functional API, with the things that we will see in the next today, in the next slides, is very powerful, and you can go quite deep using this. So whenever possible, if you have an acyclic graph, fixed graph as model, use this functional API. So let's see the standard, and no matter what kind of model how you create your model, let's see again the standard training and evaluation loops. So again, the standard workflow is create the model, compile the model, fit, evaluate, and then predict. Here is a very short example of all these steps. We will use MNIST. We will get the MNIST model as a functional API model with these inputs, 28 times 28, dense dropout, dense layer for classifier with softmax. So this function will return the model. Here is just we load the MNIST data, nothing new here. We create the model, we compile the model, again, define optimizer, loss function, and metrics. We fit the model, we train inputs, targets, how many epochs, and the validation data, and then we can call model.evaluate and .predict. So all these things are things that we've already seen, but this time you see that it can work with functional API models, and this also works with the subclass of Keras.model. So nothing really new here. Let's see how we can get a bit deeper now. One way we can change things is to use, for example, custom metrics. In most of the cases, the metrics already built in Keras will be sufficient, but in some cases, you might want to do something strange, so you have to create your custom metrics. Now we will see how you can do this. Another way to change what happens is to use callbacks. And callbacks are very powerful, very useful, and you use them all the time when you train something with Keras. And again, we will see some examples now. So first of all, metrics. This will be quite complicated, so try to stay with me. When you want to create a metric, a custom metric in Keras, first of all, you have to subclass from the metric class. So you create a class and you inherit from keras.metrics.metric. And here you have to define quite a few things. So first of all, the constructor. And then you have to create these three things. So update state, result, and reset state. Let's see. First of all, when you have the constructor, you have the name and you call the super class constructor with this name and whatever other arguments. And here, the same way as with the layers, if you remember when we subclass from the keras.layers.layer class, you have to create the state of the metric. So the metric has some state like the layers. And this state is some weights, for example, some variables, some tensor variables. So you have to create these variables ahead at the construction. And same as the layers, you can add this with the self.addWeight, okay? And this will create some tensor variables. You can pass the name and the initializer. For example, we can have the, let's say we want to create the root mean squared error. So we will create two tensors, two variables, the mean square error sum and the total samples. We will see why we use these two. We initialize this to 0, this to zeros, and this specific one will be integer. Then you have to write the update state. So in layers, you don't have to write the update state because the backpropagation is fixed, what happens. But here, we don't know what, Keras doesn't know what we want to do with the specific metric. We have to say what we want to do. So this will run at every batch. We will take the targets, we will take the model predictions, maybe sample weights. And here we have to write what happens at every iteration. So in our case, we take this and we make it one hot. We take the difference, we take the square, and then we reduce sum. And we create this mean squared error tensor. And then we add this result to this variable that we have defined before, okay? And we add this. And then we also add to the total samples, how many samples we have, so the batch size. Pay attention here that if you want to get the shape of a specific tensor, you have to use the tf.shape function, not the tensor.shape that we used in other cases. So this is the update state. Now, if you want to get the result, you have to call the result method. And in this case, what we want is to return the average for all the batches, not just the last result of the metric of the last batch, but the average of all of them. So what we do is that we accumulate all the results, and then we want to return the average, which means that we want to divide the mean squared error sum with the total samples, okay? And since we divide, we have to have the same type, so we have to cast it to float 32. This is just implementation details. The idea is that this will return the number, the final number, which is the average of all the iterations we have the update state. And another important thing is that, so this accumulates, okay, every iteration. At the end of the epoch, for example, you want to reset the state back to zeros so that it can start over again. And for this reason, you have to write the reset state where you have to reset every variable you have defined before. And you can just assign zeros, for example. So this is a way to define a custom metric, again, constructor, the update state, the result method, and the reset state method. And if you define this, then you can write any metric you want, and this should work if you inherit from this one, okay? So let me run this one first. And the good thing with this is that you can just use it as is with the compile, for example. You don't have to do something strange. Of course, you have to instantiate it. You don't pass the class, you pass the object. And you see that it works. So you see here it has the root mean squared error. So this works just fine. So let's continue. We talked about the custom metrics. I mentioned the callbacks. Callbacks, again, are very powerful, very useful. Here you can see a list of built-in callbacks for Keras. The idea of callbacks is that in different stages of the experiment, of the training loop, of the evaluation loop, of the batch, at the beginning of the batch, at the beginning of the epoch, at the beginning of the training or at the end of these phases, you might want to have access to specific things for the model or change some things for the model. And in order to do these changes or to get this information, you use callbacks. So callbacks are called at specific stages of the training or evaluation process. And here you can see some of the most common ones for Keras. So model checkpoint, this will save the model or the model weights at specific stages whenever you define it. Early stopping, the second one, which is if you want to train your model, but not for fixed number of epochs, if it doesn't get any better, you want to stop it. You don't want to keep the resources. So you use early stopping and you say if this specific metric, for example, doesn't increase, doesn't improve after, I don't know, 10 epochs, stop the training. Learning rate scheduler. So up to this point, we used fixed learning rate for the whole training process, but usually you want to change the learning rate based on specific template. For example, the reduced learning rate on plateau, you define that if a specific metric, for example, or the loss does not improve after a specific number of epochs, then you want to decrease, for example, the learning rate by a specific factor, let's say half it or 1/10, etc. So this is very useful. CSV Logger, another one that saves at the CSV file the loss and the metrics for each epoch, both for your training and your validation data. And you can create your custom callbacks, and we will see how. So again, very powerful. You will use them all the time when you use Keras for training. Let's see two examples. So let's say we want to use early stopping and model checkpoint. So this is the way you do it. You create a list with your callbacks. And in this list, we will use two callbacks, the early stopping and the model checkpoint. And you have to define specific things. For example, which argument to monitor. We want to monitor the validation accuracy, for example. And we want patience of 2 epochs, which means that if for 2 sequential epochs it does not improve, it will halt the training, it will stop it. And model checkpoint will save the model at a specific path, and we want to monitor, for example, the loss, the validation loss, and save only the best, not save all the models, for example. And the only thing we have to change is that at the feed method, when we call it, we pass this callbacks argument, the list of the callbacks. And this shall work just fine. And you see that it trains and it will actually save the best model. So it's quite slow this time. Let's wait a bit. So after that, we will wait it to finish. The idea is that because we use this model checkpoint, there is in this path that we defined a model saved. And we can load this using keras.models.load model, and this will load the best of the models, not the last one that we have right now, because this might not be the best one and previous one might be the best one. Okay, so you just have to run this and now you have the best model loaded. And as I mentioned before, you can use not only the built-in, but you can create your own callbacks. So this is a way to do it. You inherit from keras.callbacks.callback. And here you can do whatever you want. You don't even have to write a constructor if you don't want the init dunder. And you have specific methods, predefined methods that you can use. For example, on train begin is one of them. On batch end is another, or on epoch end. So each one of them has a specific signature. For example, on batch end passes the first argument, the batch number, and the second is the logs. Again, the logs is a dictionary with the loss and the metrics, okay? And you can say, okay, from logs, get me the loss argument and save it to this list, append it to this list. And on epoch end, I want you to plot this and save these plots somewhere, okay? So you can instantiate this loss history, let's say like this, and you pass it as a list when you call the model.fit, and it will make use of this list, of this callback. And on every batch end, it will run this piece of code, and on every epoch end of all your epochs, it will run this code given these arguments. And in the end, you will see that we will have all this PNG file created in the under the specific directory. So let's see, and this will just plot the PNG files that we created. So these PNG files were created using this callback that we just wrote. Now, we saw the custom metric, we saw the callbacks and the custom callbacks. Now let's go even deeper and see how we can write our own train and evaluation loops. So the standard way that we have seen is, first of all, we run the forward pass, then we retrieve the gradients given the loss, and then we update the model weights given the optimizer. So two things before we continue to see the actual code that we have to keep in mind is, first of all, the training argument. When we get the predictions of the model, the outputs of the model given some inputs, there are two modes, the training true and false. And for specific layers, the behavior of the layer is different. For example, dropout is activated when training, but not when we do inference, when we do evaluation. So when we want to do the train step, we have to turn the model argument training to true. The second thing is that the model, as we saw from the summary, has the parameters, the total parameters that are trainable and not trainable. So some layers like batch normalization have some non-trainable parameters. When we get the gradients from the loss and we want to update the weights, we want to update the weights only the trainable weights of the model. So instead of model.weights, we will call model.trainable weights for the gradients. So these two things, other than that, this is code we have already seen. For the train step, we have the inputs and the targets. We open the tape, the gradient tape, we get the predictions with training true. We get the loss function given the targets and the predictions, and then we take the gradients from the tape given the loss with respect to the model.trainable weights only. And we apply the gradients given the optimizer only at the trainable weights again. Now, but this piece of code didn't include any information regarding metrics, how we use the metrics in the train step. So let's see in more detail how the metrics work and to see how we can add them in the train step. So let's create a metric here, the sparse categorical cross entropy, for example, and we have the targets, which is number, integers, and we have the predictions, which are the one hots, okay? Now, the way we use the metrics, as we saw before, is that we call the update state. So given the targets and the predictions, we call metric.update state, and we pass these two arguments. And if we want the current average, for example, the current result, we call the metric.result, and this is the current result. Okay, so we don't call metric parentheses target predictions, we call update state, and to get the result, we call metric.result. Now, the thing is that for metrics, this is already implemented because we inherit from metric or we use a built-in. For functions, for loss functions, because they are functions and they are not a specific class necessarily, we have to do this in a different way. For this case, for the losses, we have to use a tracker. So there are different trackers. For losses, we usually use the Keras.metrics.mean tracker. And what this thing does is that we update the state, we pass some values, and then when we want the result, we get the mean, the average result from all the elements that are within the tracker. For example, let's say we have these values, we create this tracker, and we update the state with these values. These values can be, for example, the losses, the actual loss for each batch. And then the mean values, we call mean the tracker.result, the same way as the metrics.result. So we will use something like this to keep track of the loss. Now, I know it's quite new information for some of them, but these are very useful if you want to get in more depth. So try to stay with me. Now let's see the complete training and evaluation loop. So we will write a step-by-step training loop. And let's start with the training step. So first of all, we get a model. We already explained the model, different ways to build it. We just take any model. All this works for any of the three ways to build a model. Loss function, again, whatever function we want, optimizer, metrics, and here the new thing, the first new thing, is that we create this tracker, okay, which will be for the loss function. Again, keras.metrics.min. Now, this is the updated train step. Up to here, same thing. So train true to get the prediction, loss, trainable weight. So up to this point, it's nothing new. The new thing is here. So we create an empty dictionary named logs. And for each metric in this metrics list, what we do is metric.update state with targets and the predictions. And then in the logs with this name, because we have also the name for the metric, if you remember, we pass the result, okay, metric.result. And we use this loss tracker. We update the state with the specific value of the loss, and then we get the result using the dot result the same way as this one, okay? And we add it to this dictionary, and it returns the logs. Now, when we do this, we also have to reset the metrics, because if we don't reset, it will keep accumulating the results. So we have to write the reset metrics function that will reset all the metrics and also the loss tracking, okay? The same way, reset state. And let's write also the loop itself. So we get the data, just use a TF data dataset to get the batches. And for each epoch, first of all, we will reset the metrics, and then we will get the batches of data, and we will pass the batches in the train step. Remember, the train step will update the weights, etc., and will return the logs dictionary, and we can actually print this dictionary, the results. So let's run it for 3 epochs. It will take, for some reason, some time. And the idea is that then we can call logs.items, and we get the name of the metric that includes the loss and the value, okay? So this is more or less for the train part. Now we will see the evaluation part. So it's slightly different for the evaluation part because we don't have some parts. Okay, so it's completed. Let's see now the evaluation loop. So this is a test step function for the evaluation, the evaluation step. First change, training is false here to get the predictions. We get the loss, but we don't update any weights, so we don't use any gradient tape here. And more or less the same thing, we get an empty dictionary for logs, we update the state, we get the result, same with the loss tracking, get the result, and return the logs. So this is more or less the same. One difference is that we add the val underscore in order to distinguish. And same thing here, we just build the batches, we reset the metrics, and we have for each batch, we run the test step and we take the logs. And then we can print the log, the final result of the logs, okay? And this is just for the metric and the validation loss. So this is more or less how we build the test step from scratch. Now, the bad thing with this is that it's not optimized, although you can do anything you want, okay? This is Python function. It's not optimized. And if you want to make it faster, there are some ways. So even if you write your train step or loop or whatever from scratch, you can use the tf.function decorator to compile it as a Keras, as a computation graph. So the idea behind this is that if you just do what we did before, then it will run as a Python code, line by line in the interpreter. If you use this tf function decorator like this, so this is the same function we wrote before, exactly the same, but with this decorator. If you use this decorator, it will be much faster because it will be optimized, okay? It's almost half time as before. It was 1 second and something before. So this is the idea. Whenever you want to do something, you can experiment without this, but when you fix it, you can run it not in eager execution, but as a compiled computation graph using tf.function. There are some peculiarities here. I will not get in too much detail. For example, you misbehaves if you try to create some tensor variables inside the function. But generally speaking, most of the things are better with tf.function. Let's continue. So we saw that you can create these train and valuation steps from scratch, but you don't have to. Even if you want to do something strange, you can still use the fit, leverage the fit method by using a custom train loop. So there is a middle ground between using the fit as is and writing from scratch. And this is what we will see now, that you can use all the functionality that the model, Keras model provides, compile, fit, evaluation, etc., but with a custom train step. Let's see how this works. So what we will do is that we will create a new class that will subclass the Keras.model. And then we will override the train step method, okay? And we will also have to implement a property. So let's see it, how this works. First of all, we define the loss function and the loss structure. And then we don't define the train step as a function, but we define it as a method of a class that inherits from Keras.model. Here, you don't have to define anything else. You don't have to have a constructor or anything, just the train step. You want to overload the train step. Train step takes the data that is a tuple with these two things. Nothing new here. You just open the gradient tape, train true, train ample weight. So all this is the same as before. But, and here you can use the optimizer that you have defined to apply the gradients. And since you have defined a loss tracker, you can use this loss tracker to update with the current loss and return this thing. If you want, of course, you can have metrics. Another thing is that you have, in this case, to create the metrics property that will return a list of your metrics in this case. So if you do this, you don't have, for example, to compile the model. You can use whatever things you want and still be able to use your custom train step within the fit function. Let's see how, let's see how this works now. So the idea is that you can build your model the same way as a Keras, the API way to the functional API to build it, but instead of calling Keras.model, you call custom model here with the inputs and the outputs. And the idea is that here you have overloaded the train function, the train step. So you can compile if you want, and here you see that we don't define the loss function because we have defined in the custom train step. And you can use the fit the same way as before. So you gain all the functionality of the fit, which includes also multiple GPUs, distributed strategy. You can have other things, okay, all these things, but you can have also your custom train step. And it runs with no issue. So this is quite a balance between defining everything from scratch and use the fixed fit method. Now, as I mentioned, one can use the function API for this, and you just, instead of using the Keras.model, you use your custom model with your custom train step method. You don't have to write the decorator tf.function because it's within the a model, a class that inherits from Keras.model. And by passing the metrics and loss at compile, if you use compile, if you decide to use compile, then you have access to all these things. You have access to compiled loss, compiled metrics, etc. And now we will see how you can use the compile in order to access all this if you don't want to explicitly define them outside. So in this case, we will compile the model using loss and metrics, which first of all means that we have access to compiled loss. We don't have to use loss function. We can call self.compile loss. Also, we don't have to call model. We can call self here or self.trainable weights, etc. Okay. And the other thing is that you can use self.optimizer again, because we have compiled, you have defined your optimizer compilation, and you can update all the metrics, including the loss tracker. You don't have to write the loss tracker because you have compiled with a loss function. So you just call the compiled metrics update state using this, and you just return this thing. So for all the metrics, again, self.metrics includes both loss and the metrics. You just return the metric result, okay? So this gives you access to everything: compile, feed, evaluation, predict, and you can use this train step to do whatever you want within here. For example, personally, I have a fixed thing here, and I change what will be the train step every time if I want to change something here. And all this is the same as the Keras actual code. So let's see how this works. Nothing new here. The new thing, we use, of course, this custom model, create this model, and then we can compile it using our optimizer, loss, and metrics. And because we do this, we have access to this thing here: compiled metrics, self metrics, and self optimizer. So let's run this. And let's move. So this was more or less. Now we will move to the summary and then to the questions. But the idea is that it runs, first of all. So let's summarize it completed. We saw many things, and with some break within. First of all, Keras, as I mentioned at the beginning, offers a big spectrum of different workflows. So the main principle is progressive disclosure of complexity, which means that you can start with something very, very simple. The first time at chapter 2, we wrote 15 lines of code to run the whole experiment. So you can use sequential model, compile it, call the fit, evaluate, and predict, and that's all. You're going to get deeper, you're going to make changes. You can, first of all, for the model, you can use functional API, or you can even subclass. Rare cases that you usually use functional API. You want to add functionality to the training, you can use callbacks, very powerful. We saw how you can define your own callbacks. You want to use custom metrics, you can define your own custom metrics. We saw to update the state, reset the state, and get the result. You want to get a different train step, again, you can do this. You can create a model a class that inherits from Keras model and change the train step. And if you compile, you also get access to all these things: the optimizer, the compiled loss, compiled metrics, and the dot metrics. I mean, you want to do something that is completely out of the fit function, you can write your own train step, and you can optimize it using the decorator tf.function. So there are many, many things depending on how deep you want to go. You just go as deep as you want. You don't have to choose either very simple or very flexible. There is a big range in between for exactly what you want to do. And this is actually, for me, the strong part for Keras. That, okay, you can say some other frameworks lack. That was it. Thank you very much. This was the end of the presentation.